Recording is rolling. It is Friday, February 9th. Our main focus is we're going to be solving these chapter 13 puzzles. You guys remember yesterday I went through the posters thing in my room, showed you guys all those concepts, and then at the end of class we read these. I circled 7 of these. We're just going to focus on the 7, ignore the other 3. Okay. And then the poster concepts we went through would exactly answer these questions. So so far, each of my classes have had time to do 3 of them. So we're just going to do 3 today. I'll save the other 4 for sometime next week. Right? All right. Now, these 3, number 80, 84, and 90. That's what we're doing today. All right. And that'll be it. And I'll take us right to the weekend. Okay? Now, it turns out number 80 is one of the hardest questions actually asked you guys. Right? So I'm going to say that for last. Right? I'm going to do this in reverse order. Right? Because I think this number 90 with the icebergs is probably the easiest of these 3, right? So we'll do this in reverse order, okay? All right, number 90, right? You guys got paper out, ready to go? Again, my numbers are a little different than your numbers, but we got all the same premise here. Number 90, suppose density of salt water is, oh, look at that. Salt water is a little bit more dense than fresh water, right? And density of ice is, ooh, a little bit less than that of water. Okay? That's why ice floats, right? Now, most materials, if they go from liquid to solid, they tend to become more dense. Water is one of these weird exceptions, right? So ice floats. What percentage of the volume of a floating iceberg is submerged? Hey, when you guys see a floating iceberg, you guys know you're only seeing some top percentage of it, and most of it is underneath the water level. I almost forgot to mention, guys. Last few minutes of class, I want to sign off anything on your schedule that you guys need. Right? Actually, let me do that real fast. Let me just point out some things. Right. So you guys get these scheduled papers in your homeroom. You might need a signed signature. Right. And then the story with this is through your English classes. If you're 11th grade, which is most of you, it's going to be the first week of March. Right. Through your English classes, you're going to go to guidance and then get your schedule stuff in there. Right. So we'll have a couple minutes at the end of class if you need me to sign off on your science class. Right. All right. So let's get back to this iceberg question. All right, so you guys are writing this down. This is number 90, the iceberg. All right, so I'm gonna draw an iceberg. Just floating in the ocean. It's iceberg. All right, here's maybe the water level right here. Here's like the top of the ocean surface. Okay? And this iceberg has 2 forces on it. So let's get a free body diagram going. Free body diagram. Okay. Right. So 2 forces. It has a weight. That's the mass of the ice times gravity. Right. There's the weight of the iceberg. Right. And guys, what force is keeping it up?
Gravity.
The buoyant force. Right. F sub B, buoyant force. Right. Right. And wouldn't those have to exactly balance out if it's just hanging out there, just floating? Right. Right. Now, buoyant force, I remember from Archimedes' principle, and maybe you see that in a poster hanging in front of me here, right, is equal to the weight of the displaced fluid. Isn't that true? Right. Which you can further break down like this. You guys saw this over the last couple of days. Density of the surrounding fluid, I'll call it density of salt water. Right. Times volume of, I'll say volume displaced. Right. And then times gravity field. Right. So that represents the weight of displaced fluid. I'll show you guys why. Okay? So this iceberg, the submerged part, which I'm hatching in right here, is pushing that ocean water out of the way. Right? It's like creating a void in the ocean water. If you were to fill that void with ocean water and weigh it, that's exactly equivalent to this buoyant force, this claim I'm making. Right? Now, the weight of water displaced, that's mass times gravity of the water, and mass breaks down into density times volume. Okay, so that's the density of the surrounding fluid, in this case, salt water, times displaced volume, right? And then times gravity makes it a force. Okay, right, you guys get that? Archimedes principle. That's Archimedes principle, right? Now, if you look at the setup, I didn't actually tell you. Here, guys, everybody here. Right, I didn't actually tell you the mass of the iceberg, but it turns out it doesn't matter if you have like little ice cubes or medium icebergs, big icebergs. The answer to the question, what percentage is submerged, is the same, right? Like as a ratio, right? So the fact that I did not give you this mass maybe is a hint that you need to break this apart into density times volume too. Also, I gave you the density of the ice. So let's go to that. I'm going to say this is equivalent to density of the ice times volume of the entire iceberg, right, including the part that's above the ocean water, times gravity field. Okay, all right, you guys get that? Okay. Now, this upward force has to equal that downward force. So the framework for solving this is equilibrium. The sum of forces goes to 0, right? Therefore, this upward force equals this downward force. Let me go ahead and skip a step here and cut straight to this upward force, or I should say upward force minus downward force equals 0, right? So then density salt water times volume displaced times gravity field. So there's the buoyant force. Right? Has to be equivalent to this one, density of the ice, volume of the entire iceberg times gravity field. Okay, great. You guys got that set up? That's come from? Right, are we good? Right. Ooh, guys, what cancels out right here, both sides? Gravity field. Right. So remember what that means is if I take this whole system to Mars and have like floating in like an ocean on Mars, if there was such a thing, right? Would I still get the same answer in the end? Yeah, right, because it doesn't matter how strong the gravity field is, as long as it's there, and it is. Right? It doesn't matter the magnitude. Right? Now, if you look at the question, the premise of the question says, what percentage is submerged? What percentage is submerged? Right? Well, I got 4 variables. And none of those exactly answer that question, but you can rearrange it to answer that question. Because guys, percentage submerged, is that this hatched in volume compared to the entire volume? Right? Is that what that is? Right? I can rearrange this to solve for that. That's volume displaced compared to volume of the entire ice. So let's see, I can cross divide this over here, and I'll take the density of salt water and cross divide it over here. So displaced volume compared to volume of the entire iceberg is equivalent to density ice over density salt water. Right? Just like that. Right. Oh, and these are the 2 values I gave you. Okay, so here answers the question. That's equivalent to the ratio of 2 numbers I gave you. Right? Like I said, I think I want to turn this one into a poster too. I think this exact puzzle would be a really good poster. Right, so here's answer in terms of variables, and then for numbers. Now my paper says 920 kilogram per cubic 920 kilogram per cubic meter for ice. I don't know if these numbers are exactly true. Don't quote them in like a scientific paper, but they're pretty ballpark, pretty close to true, right? Or maybe it has like little sediments in it or something. And seawater, I'm using about this number, which might be, again, slightly different from your paper, possibly. I tried to pick something that was kind of reasonable. Anyway, I divide that out. I get a number that looks like this, which I can interpret as 90%. Right? Okay. You guys ever see an iceberg floating, you're really only seeing the top 10%? Ooh, hey, there's the physics of that right there. Right, right, you guys good with that? Good with that? Yeah. All right, nice. All right, number 84. An antique yellow statuette of a bird is suspended from a spring scale. The spring scale reads so many newtons. Right? Then the when it's suspended in the air. Then when the statuette is submerged in water, that force reading decreases a little bit. All right. Now, for those 2 numbers to be true, there's only one particular material that it could possibly be made out of. Right? I gave you guys answer choices and the corresponding densities of each of those materials. Right? Okay, so this is a density type question. And this kind of reminds me of the Archimedes and the crown puzzle, doesn't it? Right? Okay, yeah, you got the same question. Right? Right? Yeah. All right. There you go. All right, so I'm gonna draw this out here. Okay. Let's say I got number 84. Right. Draws bird statuette. Say it looks something. There you go, a little bird, right? Right. Now I'm gonna draw before and after. So this is before I submerge it, and then this will be like after I submerge it in this tank of water right here. Right, so I got this tied to a spring scale. Oh, spring scale right here. Right, and then same thing over here. Got the suspended, got the spring scale. Right. but different readings on those scales. Right? So let's get free body diagram going, get some force vectors. Right? Now, the first one, we're suspended in the air. And I'm going to make a little assumption here that there's no buoyant force from the air. I mean, that's maybe a safe enough assumption. Right? The force reading on the spring scale is 24.90 newtons on my paper. Right? For you guys, it's whatever I listed. Okay. Okay. Right. Ooh, guys, that means that the weight of this statuette is what? Also that same value, right? So I can say the weight is also equal to 24.90 newtons. Wouldn't that be true? Right? Okay. All right, now let's go to submerged in water. Guys, when you submerge in water, does the gravitational force acting on it, is it still the same? It's still the same, right? The earth pulling down on it, right? That's still going to go 24.90 newtons, right? But the spring scale doesn't show that. The spring scale shows a slightly smaller value, right? And my paper says 23.61 newtons. Ooh, it decreased a little bit, right? Because I haven't drawn what other force is also acting on that statuette. The what force? Buoyant force. It's going to be a little buoyant force, I'm going to do F sub B equals, right? We're all about to make a calculation right here, right? Because you guys got different numbers than I do. Right? Ooh, because if the force is summed to 0, like they did over here, up force, down force, boom, that was easy, right? But over here, now there's 3. Do you guys think if you take the difference of the weight down and the spring force up, that would tell you what's left over for the buoyant force, right? So I'm going to do that, right? And you guys can go ahead and do that too. Right? So it's that minus that, right? And I'm getting the resulting buoyant force has to be this many newtons, okay? So 2 up forces, 1 down force, and now it sums to 0 for equilibrium, right? So the premise is to solve for the buoyant force, right? Right, everybody good? Right? Okay. All right. So yeah, just gonna walk you guys through one step at a time how to solve this one. This is kind of a medium difficulty question here. Right? So now that we've solved for the buoyant force, right? I have mine, you guys have yours, right? Let's switch over to the equation for buoyant force, like from Archimedes' principle. Buoyant force equals, right? And we just did it for the iceberg. It's what times what times what? Density of the, in this case, water, because it's submerged in water, right? Times the displaced volume, right? Okay, yeah, times gravity, right? Or sometimes you see them rearranged in a different order, but okay, something like that, right? That represents, again, the weight of the water that's displaced. So if you could like take that statuette out and there's like a void there and fill it with water and weigh the water, right? That's what that says is equivalent to, in my case, 1.29 newtons, okay? Right. And you know what? We actually know 3 of these 4 variables, which means we can solve for like this one right here. Right? So the buoyant force, we just found that. So I'm gonna pop that in right there. That many newtons. That's equal to, oh guys, what was the density of water? 1,000 kilogram per cubic meter, exactly. Right. You guys remember that was back in the 1790s in France. You guys remember that was how they originally defined the kilogram? So let's call the density of water an even 1,000 kilogram per cubic meter. And so how much water it take to fill this box? There's a kilogram. And that was the original definition, right, of a kilogram. Then we're solving for, now the displaced volume would be the volume of the statuette if it's completely submerged. So I'm going to call that volume of the statuette, right, which we're solving for. And for gravity, I'll go ahead and call that about 10 meters per second squared, like I usually do. If you want to go 9.8 meters per second squared, you'll basically get same answer at the end. Right? Well, one of those answer choices will be really close. All right. So, guys got so far? Very conveniently divide, or got 1, 2, 3, 4 zeros. So I'll divide over. So the volume of my statuette is, I'm going to put the scientific notation, 1.29 times 10 to the negative 4. And that would be cubic meters because we're talking about a volume, SI units. We're going to hold on to that number. That's going to be an important number. We just figured out what is the volume of each of our statuettes, right? Okay, 10 to the negative 4. That's okay. So something really tiny was that 1/10,000. I think that makes sense too. Could you guys imagine if there was 1 meter by 1 meter by 1 meter box, a big old box? That would be a big old box, wouldn't it? Right. Okay, so how many statuettes would it take to fill that box? Okay, well, roughly 10,000. Okay. Okay, I think it is. All right, you guys ready for the next step?
Yeah.
So I know the end goal is if I can determine what is the density of the statuette, then that will tell me what material it is. Ooh, kind of like the Archimedes and the crown question. Okay. Hey guys, what is the formula for Greek letter rose density, right? So density of statuette in this case is the ratio of what to what? Mass over volume, mass per unit volume, right? Like kilogram per cubic meter, right? Right. Oh, well, here's the volume. How do you get the mass? Let's go back to the very first free body diagram setup. Okay. Guys, what is the mass of my statuette in kilograms? How about 2.49 kilograms, right? Just take the weight and divide by gravity field 10 meters per second squared, because I've just been keep rounding gravity. It's about 10 meters per second squared. Okay? So for me, 24.9 newtons divided by 10 meters per second squared gives me 2.49 kilograms, right? And that's gonna feed in right there. Okay. Here, do you have the weight of your statuette? The weight divided by 10, and that's the mass in kilograms, right? Like 1 kilogram weighs 10 newtons. Right? Okay. All right. So time to substitute some numbers. So the density of the statuette, I got 2.49 kilogram statuette occupying 1.29 times 10 to the negative 4 cubic meters. It's a kilogram per cubic meter. Maybe I'll throw that in parentheses for the calculator. 2.49. And density of my bird statuette is, I'm getting, a big number, 19,300 kilogram per cubic meter, right? Now, if I assume it's pure something, then I could just look up in a table and say, well, what material matches that density? Okay. So let's check out my answer choices. Okay. And yeah, I got, mine's gold, solid gold. Right. And then those four were, okay, so there's 4 answer choices. Right. The one on your paper could possibly be any of those. Like, yeah. So yeah, they're all choices on somebody's paper. All right, so number 80. Let's do number 80. So I told you guys to be in class. I think this one's really pretty tough, right? But I'll walk you guys through step by step, right? And then on the weekend, you guys will have this one. Right, I got a piston, has some cross-sectional area, right? So got like 0.02 square meters cross-sectional area. It closes a constant amount of gas. Okay, so imagine maybe like a sort of a sealed chamber, right? The gas is constant. Right, with a starting a volume, so many cubic meters, so 0.5 cubic meters. The initial pressure of the gas is, now mine says 101,000 pascals. I think everybody's paper actually says that. 101,000 pascals you guys have? I chose that number because, do you guys know why I chose that number? That is equivalent to one what? One atmosphere? We all of us right now are sitting in exactly that pressure. Like plus or minus a few hundred pascals. So many kilograms mass. Mine's a 60 kilogram mass, right? Is placed on top, which is going to push it down. Well, I shouldn't say the mass pushes down. Maybe the weight pushes downward, right? So that's going to be one of the steps. Convert mass to weight. Right? Push downward to new position. If temperature is a constant, which is probably a pretty safe assumption, then what is the new volume of gas in the cylinder? Do you guys think we can solve this with ideal gas law? Ideal gas law? Right. So let's go here. So number 80, zoom out, you guys can read this, number 80, right? That's the first thing I'm gonna write for this one, is ideal gas law, PV equals nRT, okay? All right, you guys remember that? Okay. So remember what this says. It relates P pressure and V volume to T temperature, like absolute temperature for some particular gas, like a compressible gas. N is the number of moles of gas. R is a constant, ties everything together. Well, it depends on what units you're working with, different values for. Okay, but that's just a constant. Okay. All right. Then I want to draw this picture. So I'm going to do before and after. Right, get a couple of containers side by side. Right, here's my containers. Right, it's got a piston. It's being pushed down. Right, we get some containers going. Right, there's my containers. Right, I have a cross-sectional area of my paper says 0.02 square meters. Right. No, here I'm going to hatch in the gas. Remember, it's a constant amount of gas. So we're going to hatch in with pink ink, some amount of gas, right? And it's the same gas right there. It's now been squashed into a smaller volume, right? Because I put this, this mass on it, which has some weight, right? Right? Some weight. Okay. You guys get that? So before, after, here, label this before, after. There you go, before and after, right? You guys good so far? Right. List all the numbers I gave you guys. So I gave you guys the initial pressure. I'll call that P naught, like the initial pressure, as 101,000 pascals. Right. And I also gave you an initial volume. So my paper says 0.50 cubic meters. Okay. Okay. And I told you this mass over here. So my mass is 60 kilograms. Oops, let me not do it twice. So 60 kilograms. Okay. Right, guys good so far? Okay. Let me give you another step that we'd have to eventually do anyway, which is, guys, if this is a 60 kilogram mass, isn't it pushing down with some weight? Pushing down with some weight, right? How much weight do I have? How many newtons? Yeah, so mass times gravity, we get like 600 newtons, right? You guys think 600 newtons, right? Something like that. Right? Oh, and I bet this gas is also pushing back with a force too. So maybe I'll just put that up there. Keep that in mind. Okay. Right. You guys good? Okay. So all the numbers I've written are given on the paper, well, except for the weight. Just do mass times gravity, get the weight. Okay. Right. You guys good? All right. Right. Now this is a process that's going to have a lot of little steps, So I want you guys to see the big picture of what we're doing, right? I mean, one of the things I want you guys to take out of a class like this is if you get a big complex problem, be able to see the big picture so that you can dive into the details and break it down into the smaller steps, right? So the big picture is this. I'm pushing down on this gas and thereby decreasing its volume. Here's ideal gas law that this is all going to tie back to, all going to connect back to, right? Guys, if you're pushing it down and decreasing the volume, what's happening to the pressure? It's increasing, right? Right. Now let's look at this guiding equation right here. Now the gas is constant, so N is constant, R is obviously constant. They said the temperature doesn't change, that's constant too. So this whole nRT is constant. So what that means is that, yeah, not only does pressure increase with a decrease in volume, but one increases with the exact same proportion that the other decreases. So for example, if the volume is 1/3 of the original volume, then the pressure has to be exactly 3 times, right? They have the exact same change, the same proportion change, just one's down, one's up, okay? Right, so that's gonna be a guiding principle there, okay? Right, maybe what I'd like to know is what is the exact change in pressure due to this weight put on here, right? Do you guys remember, here, I'm gonna do, here, I got some space on the right, I got some space down here. I'm gonna use the space on the right to solve for the new pressure. That's what I'm going to do. And then there's going to be a step after that. So do you guys remember pressure from last semester? Guys, pressure is what from last semester? Force per area. You guys remember that? Right? Like pounds per square inch, Newton per square meter, right? Pressure is force per area, right? Now, for this one, here, I'll help you guys out a bit. I'm really looking for like, what's the additional pressure? What's the change in pressure caused by this change in force acting on that cross-sectional area, right? Here's why I care about the change. Because there always was some initial pressure that balanced with, like originally balanced with the air pressure, the atmosphere. The entire atmosphere was pushing from above, but this was pushing with an equal pressure on an equal area from below, so it all balanced out, right? But by putting this weight here, it's really, that's adding, in my case, 600 newtons of weight acting on some cross-sectional area. So I'm increasing the pressure. Right? So let's get those numbers. I just increased the force. So that's a change in force. That's what delta F is, right? Change in force by, in my case, 600 newtons. Right? You guys see where I get that from? Just the weight that I add. Right? And my cross-sectional area was 0.02 square meters. Right? So I can just divide those two and figure out what was the increase in pressure. So delta P, the increase in pressure, change in pressure, is, if I divide that out, I'm getting 30,000. That would be pascals. Okay. No, that's not the total pressure. That's just the increase in pressure due to adding the lab weight. Okay. Now, the next step then is to figure, well, what is the new pressure inside here then? What is the pressure? Like if there was a fly flying around, can you imagine there's a little fly flying around inside? It's like, oh man, I feel like somebody just turned up the pressure. Like how much? Right? So, well, I guess it'd be this much change. The new pressure is equal to the original pressure plus the change in pressure. Right? You can do that for, I guess, for anything. Like last semester, it's like the new velocity is the original velocity plus the change in velocity. But now we have pressure. Okay. The new is the old plus the change, right? Okay, well, the new pressure then is equal to, well, the old pressure was, well, I had 1 atmosphere, so that's 101,000 pascals. Plus the change in pressure is right there. What we just found, pascals. Therefore, new pressure, put it all together, I'm getting this many pascals. Okay, so that fly flying around, right, feels this new pressure inside that chamber. Right. So hold on to that number. We're not quite at the answer yet, but that's an important milestone right there. We just figure out what is the new pressure inside that chamber. Okay. All right. Right. Okay. So we got to go in for the finish to answer the question, what's the new volume? And you have an answer choice in terms of volume. Right. Now, I want to do this 2 different ways. One way is, if you see this big picture with the ideal gas law, you might see you can click to the answer like in just a couple of steps here. Right. And then I'll write out the system of equations to solve it more properly. Right. So the sort of shortcut way, if you can navigate this, the big picture of this ideal gas law, you guys remember I said the proportion increase in pressure is exactly the same as the proportion decrease in volume, right? Right. So how much proportionally did the pressure just increase? And you might be able to just see, even without a calculator, my pressure went up by about 30%. You guys see that? Right. And so I'm going to do this part just on my calculator screen, and then I'll write something down later. Right? But I'll show you guys the answer here. 131 kilopascals compared to 101 kilopascals. That's an increase of, it increased by a factor of 1.30 basically, right? I said, right? All I did was that the new pressure compared to the old pressure, just divide those two. I got a ratio of 1.30, right? So I'm saying the pressure increased by 30%. What that means is that the volume decreased by 30%, and that'll lead me straight to the answer. So all I have to do is take the original volume, which for me was 0.50 cubic meters, and say divide by a second answer, which was 1.30. So I'm dividing by 1.30. So I know the volume definitely shrunk. In my case, it went down by a factor of 1.30. Right. So the answer is 0.39 cubic meters for my paper. Okay. Right. So all I said was the pressure went up. Here, divide these 2 pressures, new compared to old. It gives you a factor of 1.3. Yeah. That was given. It's not straight on paper. Yeah. Okay. So the fact that my pressure went up by 30% means that the volume had to decrease by 30%. So I take the original volume, divide by 1.3. Got the answer. Right. Now, let me go solve this a little bit different way. I'm going to solve this with a system of equations. Right. So I want to see this written out. Right. The equations could look like this. Pressure initial, volume initial equals nRT. Pressure new, volume new also equals nRT. The same N, the same R, the same T. This right here is a system of equations. Hey guys, system of equations. Is it okay? Is it perfectly fine mathematically if I divide one equation by the other equation? I could do that. Right. You guys, what is nRT over nRT? Is that just equal to 1? Right. They're all same value. That's 1. can I cross multiply this P and this V? So I'm saying P original V original is equal to P new V new. I think it's Boyle's law, I think it is, right? Like that. Embedded in ideal gas law. And I know 3 of these 4 things I can solve for V new. So I got 101,000 pascals at 0.50 cubic meters equals the residue pressure I just found right here. So I'm going to substitute right here, 131,000 pascals. Solve for V new. Very simply divide by 131,000 pascals. Okay. So 101 and 131 all times 0.5. I'm getting V new is the same thing I just showed you guys was a minute ago. 0.39 cubic meter. All right, which is an answer choice on my paper, and that is the answer right there. All right. Yeah, so that was a pretty long journey right there. But hope you guys enjoyed that one. All right, so we got a couple of minutes. Walk around, sign any sign paper schedules you guys need, and yeah, that is a wrap on the week.